My talk is a result of our joint work with my students, Jamshed Rakhmatov and Sukhrov Ushkarbekov from National Academy of Sciences of Tajikistan, Tajik National University, and Tajik State Pedagogical University in Dushanbe. I'm sorry for one issue. I changed the title of my presentation. And first step, I want to talk about fuzzy stochastic differential equation, but not so ready for this. And today I talk about fractional stochastic conduction, fractional stochastic heat equation of hyperbolic type, not parabolic type, hyperbolic type. I talk about it. This model, this classical model of heat conduction, 1.1, where Q is at a heat flux, T is temperature, lambda is gradient operator. In the case when there are no heat sources, the law of conservation of energy have a following form: 1.2, where T is time, rho is density, C rho is specific heat conductivity of the medium body. When we substitute 1, 2 into 1, 1, we obtain the classical heat equation and the form 1.3. Okay? Where D is coefficient of thermal conductivity, delta is Laplacian, and or D in general case. The heat conduction is a parabolic type of equation and has a paradoxical non-physical property. Infinite velocity of propagation of disturbances, which indicates this kind of conduction equation have property like infinite velocity of propagation of disturbance, okay, of disturbance, which indicates a very narrow field of application of Fourier law. A natural question arises as to how to correct Fourier law so that the corresponding model shows a finite perturbation provocation velocity. This is a question, okay? This question formulated here, the question formulated here was answered in the early 60s by French mathematicians Cattaneo and Vernet. This is French mathematician. They proposed to use, instead of 1.1, instead of heat equation, instead of Fourier law, another differential model in the form of 1.4. Flux, he proposed take flux like this, minus A lambda T, T is the temperature, minus tau derivative from flux of T, where tau relaxation or delay time. We can see in the model 1.4 differs from the Fourier law by the presence of additional non-stationary term proportional to value of tau. At tau non-equal to 0, 1.4, from 1.4 we obtain the hyperbolic heat conduction equation, namely 1.5, okay? Not parabolic heat equation, but we can write hyperbolic heat equation like 1.5. This model, 1.5, demonstrates a finite speed of perturbation propagation and is widely used to solve various problems in the theory and practice of heat and mass transfer. I talk about literature and about references at the end of my talk. Note that in mathematical physics equations, equation of the form 1.5 is called the telegraph equation. And essentially, the Cattaneo-Vernet model is a differential difference analogous to Fourier law, and as the form 1.6, like this, where the left part of the equation is calculated at t plus tau with shift. The shift is quantity of shift is tau. At tau is equals to 0, the differential difference relation transfers into the Fourier law 1.1. If we formally decompose the left part of 1.6 into series over tau and keep only two main terms of the expansion, we obtain the Cattaneo-Vernet model. We want to note that in recent decades, there has been a rapid growth of the theory of stochastic partial differential equations with fractional orders of derivatives both in time and in the spatial coordinates. This is primarily due to a wide range of application in physics engineering in such areas as electromagnetism, fluid mechanics, signal propagation, hydrology, functional kinetics, electrochemistry, viscoelasticity, optics, robotics, biomedicine, etc. Many publications are devoted to the functional heat conduction, fractional heat conduction equation of parabolic type. Very few works refer to heat conduction equation of hyperbolic type. Stochastic partial differential derivative equation, stochastic partial derivative equation of fractional order in time considered in one work of Oxendahl and his students, 70. Our paper, in this paper, we consider a fractional stochastic equation of hyperbolic type, namely equation 1.7. Here we have tau relaxation time, d alpha over dt alpha. This is derivative Gerasimov-Kaputov form of order alpha. Alpha belongs to 0 till 1. 1 is included too. D is a positive coefficient. Sigma is belong to OR. This is also constant. And du is a Laplacian operator. WTX, like 1.8, is white noise in time and space, in time and space, not only in time, but in time and in space. And we can write like BTX is equal to BTX omega. T is a non-negative, X belongs to OR-D, omega from capital omega. This is the Brownian sheet with probability low p. The boundary condition of the form 1.9. Here, delta 0x is point mass and 0, and in 0 it is like Dirac functions. And also we have in infinity, minus infinity, plus infinity, we have a condition 1.10. The fractional derivative in stochastic media is more useful in comparison with the integer order derivatives in many situations. For example, in the analysis of propagation of signals and waves, including ocean waves around oil platforms, and in the study of ultrasound properties in solids. In particular, the fractional heat conduction equation in stochastic media of the form 1.7 can be used in describing an anomalous diffusion, subdiffusion, or superdiffusion of heat flux propagation. It is connected with the power conversation law. I'm sorry, this is a mistake. The power conversation law. Our paper consists of introduction, several sections, and conclusion. Section 2.6 gives some preliminary information and some auxiliary results. Section 7 is devoted to analyzing the properties of the Fourier Laplace transform. Section 8 established the uniqueness theorem for the solution of problem 1.7, 1.10, and derives an explicit representation of the solution. First of all, I want to talk a little bit about space of temporary distributions. For the convenience, for our convenience, let us recall some basic properties of the Schwarz space of rapidly decreasing smooth functions, the space of basic functions, and its dual space S prime of temporary increasing distributions. Let n be a given natural number. Let S is equal to S or n be the space of rapidly decreasing smooth functions. F on Rn equipped with form like this, norma F K alpha, like this, supremum, where K is a natural number and 0. K must be 0. Alpha is multi-index, like this. Under the above conditions, S will be Fréchet space. Let S prime, I'm sorry, is a dual space for S, the so-called space of temporary growing distributions. We denote by B the family of all Borel subsets of S prime, equipped with weak star topology. If F capital belong to S prime and F belong to S, then we can use this kind of functional 2.1, which denotes the action of phi capital on F. Here, few examples about temporary distributions and derivative of temporary distribution. I don't talk about it. I think it is more or less known for you. Then I want to talk about some properties of beta-Leffler function. It's also very, I think, very known results. Two parameters function, beta-Leffler, like 3.1. If we take P beta is equal to 1, we find 3.2. And I want to note that E alpha of Z is equal to E alpha 1 Z, and E1 is an exponential function 3.3. Then I want to talk about Gerasimov-Kaputov fractional derivative. Here we have a presentation yesterday about like this kind of fractional derivative. This kind of fractional derivative is the convolution function G alpha t with h like 4.1. We have a relation 4.2 defines the fractional Gerasimov-Kaputov derivative of order alpha of the function ht. If the function h is non-smooth, these derivatives are interpreted in the sense of distributions. This is example. When ht is t, we can calculate this functional derivatives. And also recall the Laplace transform L is defined as equation of the form 4.5 for h, which the integral in 4.5 is convergent. Here, some formulas of the Laplace transform for fractional derivatives for Mittag-Leffler functions, and also convolution theorem for the Laplace transform, like 4.12. Now, we need to talk a little bit about white noise and time space. Let n be a fixed natural number, and let n is equal to 1 plus d, where d is a dimension of r, here rd, or t. Let us define omega like s prime, equipped with weak star topology. This space will be the base of our basic probability space, in the sense that the probability measure will be defined via the following theorem. This is a classical theorem, Bochner-mean loss theorem. Mean loss, I'm sorry. It's mistake. Mean loss theorem. There exists a single probability measure P on B of S prime or N with the following property. For all phi from S or N, where phi is equal to phi to 2, and Rn, this is a Euclidean norm, is an action omega on phi, omega phi, and through E is equal to EP denotes the mathematical expectation with respect to probability P. We will say that the triple S prime, BS prime, P is called the probability space of white noise, and P the probability measure of white noise. Here, a few properties of white noise in time space. I don't talk about it. Next, also, this is a continuation of white noise properties. It is easy to see that using the Bochner mean loss theorem, we can find construction of m-parametric motion for any n. Moreover, we obtain a representation of the space omega is the of the space omega is the Fisher space S prime or n. This leads to success in many situations, such as construction of Haida-Malavin derivative, which can be viewed as a stochastic gradient on omega. This is also here we have a definition of white noise, time space Brougham motion, also called Brougham sheet with a probabilistic low p. So the process is Tx continuous almost surely. We can define for almost omega is from capital omega is derivatives with respect to t and x and the sense of distributions. And this point we can talk about Fourier transform of the solution we need in future, and we talk about Fourier transform of the solution at d is equal to 1. In this case, we have an equation like 6.1 with initial condition 6.2 and also condition 6.3. We consider the Fourier transform like 6.4, which satisfies this kind of equation, 6.5, with initial conditions 6.6 and 6.7, integration 6.5 with condition 6.6 or 6.7, we can be carried out through Laplace transform interpretation of the form. We have a Laplace transform here, and also we have a Fourier transform here. Sometimes we can talk about Fourier Laplace transform, 6.8. We use fractional Gerasimov-Kaputov derivatives, which allows us to consider initial conditions in terms of integer order derivatives. This allows us to obtain the following formula for the Laplace transform of derivatives, like 6.9, where m minus 1 is equal to this number less or equal to integer part of alpha. Formula 6.9 is established as follows, like here. We can write this formula. We use Laplace transform, and we can write for ut beta this formula. Then we use well-known formula for Laplace transform of integer derivatives like this, and we obtain 6.9. It follows from 6.9 that since ut or 0 beta is equal to 0, there is no difference between the cases. Alpha between 0 and 1 over 2, and 1 over 2 less than alpha, less than 1. Sorry, here 1. After some calculation of the basis of 6.9, we will see that the Laplace transform of solution of equation 6.5 taken into account the initial condition leads to the formula 6.10. The problem of finding an inverse Laplace transform for the homogeneous equation 6.10 10 at sigma is equal to 0 is solved in the following theorem. This theorem for deterministic part of our equation, the Fourier transform of solution of problem 6.2 and 6.3 changed, can be written in the following equivalent forms, where H1 this number and H2 like another number. We have a presentation of Fourier transform for our problem. Next, we can talk about proof of this presentation. It will be convenient to write 6.10 as follows. Then we apply relation like 6.13, it is the properties of Mittag-Leffler functions. And then we can write 6.14. We can see that this 6.14 valid for H greater than eta G. Okay. This section 7 belongs to properties of Fourier transform of our solution. I move. Okay. Now, in section 7, we have explicit solution for only alpha is equal to 1, 2, not for all alpha, but only for alpha 1 over 2 of the heat conduction equation of hyperbolic type. We have a theorem like 7.1. Okay, I don't talk about proof. Also, we have a theorem 7.2 about distribution obtained using the Fourier transform inversion 7.1. We can take following form for U1 over 2 Tx. And theorem 8.1, we have a presentation for solution of our equation, our original equation, is form and U is equal to E1 plus E2. E1 is 8.2, E2 is 8.3. Also, we can give proof. This is references. First part of my references devoted to application. Then this theoretic monographs or papers. Very important for me. This is a Kodinov paper. Kodinov. Okay. Thank you for your attention.